Alright, I'm recording this video still on September 7th, but I just recorded the video for the 7th there, and we'll say this is the 8th now, so let's just go to a new page. I have infinite paper anyway. So for 9/8, that would be Thursday. So welcome to Thursday, guys. You're now in the present. I'm currently recording this in the past. Theoretically, if everything's going to plan, you have finished a homework assignment from yesterday, and now you're going to do another homework assignment today. I don't think you need any help. So today I just want to do something that's fun for me, and it might be fun for you. I'm going to go ahead and wager that maybe 1 out of the 5 of you might have fun. So maybe not anyone. But this is something that I value, and I want to show you. So I want to talk about infinity today. You guys are ready to talk about infinity. You're 8th graders. So in math, we have something that's called listable. It's a type of infinity. It just means you can put it on a list. That means if you're thinking about, you have like a train, right? So here's my terrible drawing of a train. There's maybe the cylinder and it comes down. I don't know. There's my choo-choo train. Maybe it has a smokestack coming off. Choo-choo. And there's the smoke coming off of it. And then it has a bunch of cargo cars, etc., etc. And then there's people on those cars. The whole point here is, could I have a list of all the people that are in the train? The train might go on forever, but if there's some systematic way of going through and listing every single person, then it's called listable. And some types of numbers are not listable, and you can actually prove that they are not on a list. If I have enough time, and if I'm feeling energetic enough, it's already midnight, 12:13 right now. I want to show you what it means to be listable. So the general idea behind if something is listable, this is a very complicated idea in mathematics. It means you have some sort of one-dimensional list. So that means the list goes in one direction. So for example, I'll have a list that goes from left to right. You have like we'll have like a start number right there, and then you have the next number, and then the next number, and then the next number. You are not allowed to have a list that goes, so you're allowed to have a list that just goes from the start to the right, but you can't have a list that goes both left and right. It has to have a start. It might not have an end, but at least it goes in one direction. That's what I mean by one-dimensional. You can't go left and right. It can only go to the left. And it also has to have some clear pattern. If I showed like my son Riley the pattern, he should be able to kind of figure out the pattern. It should be a pretty clear pattern. It can't be like do 7 and then 9 and then 13 and then 26 and just some dumb pattern that no one can understand. So as long as you have a list of numbers, it might go to infinity, it might go on forever and ever and ever, and there's some clear pattern, then it is listable. And I can already hear the voice in the back of your head asking, why should I care? It's because some numbers are not listable, and it's interesting. I hope it's interesting to you. It's interesting to me. Let me show you that the natural numbers are listable. It's kind of an easy thing to do. So natural numbers, as a review, natural numbers are also sometimes called the counting numbers. And just take a look at the list. It goes 0, then 1, then 2, then 3, then 4, and on forever and ever into infinity. By default, the natural numbers are listable. I mean, look at this. It has a start. It does not go in this direction. So you say, no, it doesn't go in that direction, and it goes to the right forever and ever. It is listable. Pretty straightforward. It has a pattern. I could, like, you know what the next number is? It's going to be 5. You know what the next number is? It's going to be 6. You know what the next number is? It's 7. Like, so I'm just checking these off, right? It has a clear pattern. It has a start, and it can go on towards infinity. It has all of the conditions to be listable. So let's try something a little bit harder. What about integers? The next level up, right? Integers, we had natural numbers down here. Integers are the next level up. Are integers listable? Are rationals listable? Are real numbers listable? One of those is not, by the way. Let's figure out which one, right? So let's look at integers. And I think I already said this in the video, but it's late and I might have forgotten that I said this, but this video will not help you at all with the checking your understanding. I'm purely doing this out of fun, and I'm hoping that you'll have fun too, but who knows. So natural counting numbers, let's do this all in caps in red. This is important. This is listable. I can have an infinite list. Is that listable? It looks right. All right, what about integers? So coming back here, so that was number 1. What about number 2? Integers. Are integers listable? Well, that's a problem, because when I start working with integers, I get 0, 1, 2, 3, and right now it looks like I'm in good shape, right? I have a beginning, and it's going in one dimension, but then you start getting into a problem. You're like, oh shoot, -1. Oh no, I'm going in 2 directions. I'm only allowed to go in 1 direction. -2. Oh, -3. You're not allowed to go in 2 directions. So is there a way that you can change 2 directions into 1 direction and still have a clear pattern? And I know that this is a new idea of what it means to be listable. Some mathematicians use the word countable. Ugh, it makes me want to barf. Countable. I hate, yeah, so that is the official term, and there's some official terms that I like. That one just does not make sense, because you can't count to infinity. Infinity never ends, but you can put them on a list, so I call them listables. So integers seem at first like they cannot be listables, because you can't put them on a list that goes in 1 dimension. It goes in 2 dimensions. So here is how you can change that. Watch my pattern, and if you can find the pattern and you agree that it only goes in 1 dimension, then it's listable. Start with 0, then do 1, then do -1. All right, so far so good. Then do 2, then do -2, then do 3, then do -3, then do 4, then do -4, then do 5, then do -5. Do you guys see the pattern? Because again, I'm just going off of the criteria. Is it a one-dimensional list? Does it have a start and go into infinity? It has a start. It does not go to the left, so that makes me happy, right? It does go just in 1 dimension. So, I mean, that one gives us a huge check. But is there a clear pattern? And I would argue, yes. Couldn't you figure out the pattern? What do you think the next number is, guys? What do you think the next number after that is? If you can fill in that pattern, I think it's clear enough that the pattern is there, right? And ta-da! I did some math magic, but it is now listable, and it seems like that's a silly thing to do, but it's cool to say that this is listable. I have an infinite list of integers. All right, here is one of my favorite proofs. It definitely makes the top 10 list of all of my favorite proofs in mathematics. This one is testing whether or not, number 3, fractions, also known as rationals. Rationals, and I'll put in parentheses, fractions. Are fractions listable? And it seems like the answer is probably no. And let's run with that. Let's go ahead and say no, because look at this. We had up here a list that went to the left and to the right, and we want just a list that starts here and only goes to the right. Look at the problem with rationals. If I want to write down every single possible fraction, this is how I do it. I would start by saying, I'm going to write really small. So I'm going to like zoom in here to the squares, because I'm going to have a lot of fractions. 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7. And at first look, I'm in good shape, right? I have a list that had a clear beginning, and I'm going in 1 direction. If I go like this forever and ever, I will be okay. Like, it's a clear pattern. But here's the problem. When in this pattern will I ever get 2/3? Shoot, right? Oh man, we're out of luck. There's no way that this pattern is going to generate that. It will keep going with 1 over 8, 1 over 9, 1 over 10. I need to list all the 1 over infinity numbers on the bottom first. So I'm going to make a second list where I do 2 over 1, 2 over 2, 2 over 3, 2 over 4, 2 over 5, 2 over 6. I think you get the point. I'm just going to do dot, dot, dot. It goes on forever and ever, where that bottom number, also called the denominator, is going to continuously get bigger and bigger. And when I'm doing this, you're probably thinking, like, Mr. Sindel, you are doing this wrong. You are going in this direction, and now you're going in this direction, and this whole area is going to be an infinite area. And I'm going to say, yes, yes it is. But check this out. I'm going to keep going. You might not have figured out the pattern yet, but the next one I'm going to do is 3 over 1, then 3 over 2, then 3 over 3, then 3 over 4, 3 over 5, 3 over 6, dot, dot, dot. So all I'm doing right now is I'm trying to make sure that you can understand my pattern. Can you figure out, for example, what I'm going to put in that cell right now? Look at the pattern. 1 over 1, 2 over 1, 3 over 1, and you can now probably see it 4 over 1, and then 5 over 1, and then 6 over 1, etc., etc., etc. And then what I do from there is I just increase that bottom number. I go 1, 2, 3, 4, right? So this is 1, therefore the next one is going to be 2, so it's 4 over 2, 4 over 3, 4 over 4, 4 over 5, etc., etc. Kind of same thing down here. 5 over 2, 5 over 3, and I'm just going to do dot, 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 dot. 6 over 1, 6 over 2, 6 over 3, dot, dot, dot. But because I think that you can see the pattern, I'm going to just go dot, dot, dot. And usually what people do, what mathematicians do when they have this giant diagonal of dot, dot, dots, they have like one really big dot, dot, dot diagonal. It goes on forever and ever in the diagonal direction. All right, so what I'm trying to do now is I want to show you that I have written down every possible fraction. If I continue this table for infinity, that direction, that direction, that direction, that direction, if I go to infinity, I will write down every single possible fraction. That is a rational number, right? Irrational numbers, I don't have any square roots. There's no way to add irrational numbers to this, which is fine because I'm only talking about the rationals. I've written down every possible fraction. The problem now is, how do we get this two-dimensional table of an infinite number? It feels like it's an infinite more infinities than the previous one. How do we somehow have a pattern where I just list numbers with a start and only going to the right? I'm not allowed to go down. I can only go to the right. How would I possibly do that? And here is the genius. Remember when I talked about Lockhart's limit, like that beauty of mathematics? Here's the most beautiful idea. Diagonals. Here is my pattern. And I'm going to do this in a different color so it stands out. My pattern says this. I first will go this direction. And I'm going to continue this in a sec. Let me maybe zoom out a little bit. The first number on my list is 1 over 1, comma. The next numbers on my list are going to go this direction. So it's going this direction first. And then I'm going to list 1 over 2, because that was the one that I just did right here, right? 1 over 2. The next one's going to be 2 over 1. The next number is going to be 2 over 1. The next number is going to be, and you kind of can see, it's going to loop back up this direction. It's going to go diagonal. The next number is going to be, 3 over 1, and then 2 over 2, and then 1 over 3, and then, so I'm going to keep coming up, and then down the next diagonal. I'll come down this direction, and then I'm going to have 1 over 4, and then 2 over 3, and then 3 over 2, and then 4 over 1. And here's the trick. Again, I have to have some start, some pattern of numbers, and I'm allowed to go on to infinity as long as you can figure out, you the student can figure out what the next number is going to be right here. Then I can prove that this is listable. And remember, you have to hit every single number. You can't just skip a number. You're like, 2/5, we're just going to exclude that from the list. No, every single number has to be hit. And I guess I should have put that in my definition. I'm a terrible teacher. I apologize. Every number has to be hit. You can't just skip some. And I think you can agree. If I start shading in numbers like this in the table, I will hit every single fraction in here. And I've done it in a way that you can see the pattern, and I've listed it in just one dimension out to the right. It's so beautiful. I get like stuck on like how cool of a proof that is. So believe it or not, even though it seems like there's so many more numbers, you can still find a way to put them on a list of passengers for your train. It's an infinite list, but it's still a list. So this one, believe it or not, is listable. do I have the energy to talk about reals? I'm going to try it. So, just as a review of where we've gone today, we have talked about what it means to be a listable. I have a kind of weird definition here. Natural numbers by default are listable. Integers were listable. Rationals were weirdly listable. The next rung up, we've done this one, listable. That one's listable. That one's listable. What about the real numbers? Well, Mr. Snell, you did it in a different color, so it's probably different. And I mean, that was random, but it is different. Let's see if I can try to remember how to do this. This is also testing Mr. Sindel's capabilities. What about the real numbers? Number 4, the real numbers. Are they listable? I'm going to prove to you that they're not. And when I use the word prove as a mathematician, I really mean like you should know in your bones by the end of this. Like there's no way around it. It's impossible to have a list. So let's go ahead and do this. I'm going to make a list of numbers. So I'm going to have a list like 0.135972639 I don't know. And then I'm going to have a totally unorganized list. There's no structure. Like over here, there's this beautiful structure of, go along the diagonals and, just go left and right and combine it into just one direction. There's beauty to this one. This one's just like, throw them all together, guys. Throw them in the blender. 0.983251234 I'm creative with my numbers. 0.23568 2, 4, 6, 8. Who do we appreciate? 0. I don't know. 0.0000135 with some more zeros. Like, okay, I'm just putting like a bunch of random numbers. Let's pretend that this list goes on forever and ever and does contain every possible real number. That means it includes rationals that don't have any pattern with them. It's like, I should have put pi in there right here. I gotta go back here. It includes 3.141592653 Again, all these numbers could go on forever. Theoretically, I could go on forever and ever that direction, ... And now, theoretically, I'm going down forever this direction. So we somehow have found the holy grail. This list contains every single possible real number. Let's assume that. And I'm going to show you a number that isn't on your list. And by showing you that I have a number that isn't in your magical list, that's impossible, right? I just told you. This is the assumption. We're assuming this. Assume the list has literally every real number. That means it has a square root of 2 on it somewhere. It has a pi. It has an e. It has a phi on it. It has every number, square root of 7. Every single number is in this list. So what I'm about to do is I'm going to show a number that isn't on the list. And stay with me, because that's mind-bending. Like, Mr. Sindel, you're so silly. You already told us it has every number. How can you show us a number that isn't on the list? Because we already know that every number is on the list. This, in math, is called a contradiction. So this is called a proof by contradiction. And it's used all the time in math. It's like saying something like, this number is even, and this number at the same time is odd. And you're like, God, you're dumb. Like, no, that can never happen. And here's the thing. You're right. It can never happen. You can never have a number that's even and a number that's odd, because that is impossible, which means the original claim is impossible. That's the powerful thing about the proof by contradiction. I will repeat it now. I'll write it down because this is important. if you have just one assumption and something literally impossible happens, that can only mean one thing, and this is in red, in all caps, then the assumption was wrong. With like triple exclamation point. That is super cool, right? Like, I'm going to say, I don't know, what's the non-mathematical equivalent? You have to be careful because when you step outside the world of mathematics, very few things are impossible. I'm drawing a blank. I'm going to blame the time. It's currently 12:32 past midnight, but that's the general idea. So I'm going to show you, we're going to assume every number's on the list, and then I'm going to show you a number that isn't on the list. These two things are impossible to happen at the same time. It's like saying I am 6 feet tall and I am 5 feet tall. Nope, you can't do that. It's one or the other. Whatever you've assumed at the very beginning, your tape measure is correct, is the assumption. Well, nope, your tape measure is incorrect, sir. Whatever assumption that you had, it has to be wrong. All right, so there's our magical list. Let's try to find a number that isn't on that list. So here's the thing, and this is where my proof of this is, I'm trying to remember. I'm pretty sure that every single time I see a number, do I like add 1 to it? I think I go down the diagonals and I add 1 to it. Let's go with that. I think that'll work. I might be wrong here. I apologize if you're watching something that is incorrect. I'm going to look at this first spot, and let's go with that number. I don't know, it could have an infinite number of numbers, but I think every number can eventually be divided by such a big number that turns into a decimal. But I'm going to look at that number, and I'm going to add 1 to it. So 0 plus 1 is 1. I'm going to have a decimal, and then I'm going to look at the next diagonal number, and I'm going to add 1 to it. And, well, 9 plus 1 is nothing. It's 10, so I'm just going to call it 0. Sure, why not? I'm going to choose that number. That's a 3. Let's just add 1 to it. It's going to be a 4. And then I'm going to choose that number diagonally, and that number is 0. I'm going to add 1 to it. So 1. I'm going to choose that number. It's a 5. I'm going to add 1 to it. It's a 6. And I'm going to do that infinitely many times. I'm going to do this down and down forever to the bottom right. And you're allowed to count to infinity. I'm allowed to have infinity to the right, infinity down. I will have, by the end of this process, a number right here where this number is different from that number, so these two can't match. This number is different from that number, which means these two numbers cannot match. This number is different from this number, which means these two numbers cannot match. This number is different from this number, which means these two numbers cannot match. This number is different from this number, which means these two numbers can't match. And if you do this for an infinite number of numbers, this number will not be on that list. Let's go back to my claim. I assumed that every real number is on that list, but by doing this cool little adding 1 and going diagonally to change every single digit so that you're making sure that number can't be on the list, that number can't be on the list, just digit by digit by digit by digit, you have made sure that this brand new custom designed Gucci number is not going to be on your list. And that's a contradiction, because I assume every number is on the list, but there's a number that isn't on the list. That's like saying I'm 6 feet tall and then I'm 5 feet tall. You can't have both. It's one or the other, sir. And that means that it's impossible, which means the original claim was impossible, and therefore, real numbers, they are unlistable. Which means something really, really powerful, but I'm I'm feeling tired, and I haven't even recorded the videos for 7th grade yet, nor for the lessons I have to do in Yosemite. So I'm going to end it right there. Speaking out loud now, I don't know if this video even is going to go this far. I might edit it out, but I'm lazy, so I'll leave this in. But I think if today is Thursday, I'm thinking in the future, then you're going to keep working on a homework assignment that's review from yesterday. You can rewatch that video if you need to. And on tomorrow, on Friday, I want to do a fun pattern activity. And I have all the materials sent and emailed to Miss Sasson, to Miss Dulce, to all the people that will need it, to give it to whoever's subbing. I don't know who's subbing. I haven't looked at the calendar. And hopefully that will be fun. There's going to be... Maybe I'll do a video introduction. Sure, I'll do a quick video introduction if I have time. But for those of you that watched until the very end, you're the best. I want to give you a sticker, but I can't verify that you're the one that watched the very end. I just really appreciate it. These are some really high-level topics that I didn't learn about until I was in college. And I'm somehow thinking it's a good idea to teach to 8th graders. I don't know. You can give me some feedback when I come back on Monday after the weekend. Like, this is I had no idea what you're talking about. Yeah, sure, that's fine. Just be honest with me. But I had fun recording it, and I had fun remembering it. I'm having a feeling that my proof here for this real numbers is a little bit off, but the general idea is pretty on it. Thanks for watching. I'll talk to you guys on Friday. I'll record that video, right? Bye.